All right, 9.2, why do only some things dissolve? This is an interesting question because, if you think about it, for example, if we mix water with sugar, the sugar will get dissolved in the water. If we mix salt in water, the salt will similarly get dissolved in the water. However, if you put sand in water, for example, that will not get dissolved in water. And so the question naturally is why? Why does salt and sugar dissolve in water, but sand doesn't? And so the simple answer here is that like dissolves like. Only things that are like each other are going to dissolve each other. So for example, charged things will dissolve charged things, or uncharged things will dissolve uncharged things. However, something charged will not be able to dissolve something that's uncharged. And what we mean by charged, we're talking about polar, ionic, and nonpolar. So bringing back some things from the past. You're going to need to know those definitions and review that in order to be able to do polar, ionic, in order to be able to determine if something dissolves one another. Now, just a quick review for you guys, right? How do we know what something is? Right, like, is it polar, non-polar, ionic, covalent, right? The first thing is you have to break it up into ionic versus covalent. And something is covalent if it's a metal, sorry, my bad. If it's a non-metal with a non-metal, right? So two nonmetals, two things on the right side of the periodic table, if you have them together, you have a covalent bond. Versus if you have a metal with a non-metal, two things from opposite sides of the periodic table, that's going to be an ionic bond, right? And therefore an ionic compound. And if you have an ionic compound, therefore your molecule is going to be ionic. And so, yeah, it's just ionic. I guess there's nothing actually after that, right? But covalent, it could be polar versus non-polar, remember? And so how do we know if something's polar? Well, there's two things, right? For one, there needs to be a difference in the electronegativities greater than 0.5, right? For at least one of the bonds, there needs to be an electronegativity difference of greater than 0.5. If all of them have an electronegativity difference less than 0.5, it's going to be non-polar, right? You have no chance of poles, really, right? But not only do we need to have poles, right, to have electronegativity difference greater than 0.5, but we need to have also an overall net pull. And so the poles cannot cancel each other, right? So those are the two conditions for polarity. Versus for nonpolar, either the electronegativity difference for all of the bonds is less than 0.5, or if there is a net pull, the net pulls cancel, okay? So those are the things that make it nonpolar, right? And so go through this flowchart for each molecule, determine if it's ionic, polar, or nonpolar, and then use that in order to determine, apply this rule, like dissolves like, to determine if things dissolve. And so I thought it'd be best to go over some examples with you guys. Let's take a look at this one that I did for you guys. Salt in water. Salt, it looks something like this. Remember the lattice structure, right? The lattice structure means that we have NaCl, Cl, Na here for salt. And then we have water, and water has that nice Mickey Mouse bench shape, as we've mentioned before. And remember that salt, we can do it here. Salt, remember, it is ionic because it is NaCl, right? Metal, non-metal. And so therefore it's ionic. Water, whereas it is H2O, that's non-metal, so it's covalent, and it is polar, remember, because the electronegativity difference between H and O is greater than 0.5, and there is gonna be no canceling of the pulls, right? There's an overall pull here to oxygen. And so water is polar, and therefore charged. Salt is ionic and therefore charged. And so here, salt and water, I guess we can answer this question first. Are they going to be, sorry, sneezed. Are they going to be miscible? Can they mix together, or are they going to be immiscible? they're not going to be able to dissolve one another, right? They're going to be miscible, right? Like dissolves like, charged, and so they're going to be miscible. They're going to be able to dissolve each other. And so as a result, the difference between our not stirred and our stirred is that when you have things that are miscible, that dissolve, right? Basically, the Na and the Cls are going to get separated out. And I wish I had I wish I had a color copier. Unfortunately, I don't. But if I did, we'd have some color here. And what you can see, right, is that the Cls got separated out with the NAs, right? And so we have the Na and the Cls getting separated out by the waters. We're kind of like preventing them from being next to each other. And that's what dissolving is, right? Dissolving is when things get separated out, they get spread apart inside of the solvent. And so that's what happened. That's what happens with salt and water. The water, because it's charged, is able to attract the charged Na and the Cls and pull them apart. So this is miscible, and it's also therefore a solution. If you have dissolving, you're going to have a solution. And so, whereas if it's immiscible, it's going to be heterogeneous mixture. So let's go on to another one, sugar. Now do note, this is a very complicated molecule, and so as I mentioned here, you can just use a simplified version of sugar. Now you could just draw I'm okay if you just draw C6H12O6 like that. Even better though, just because I like chemistry, is technically this is an octagon shape, right? And so, sorry, hexagon. And so, you could draw it just like that. And then also there's an O here. And so that would be an even better simple drawing. But, if you just want to draw C6H12O6, that's okay. So, just to make it easy for you guys, I'll do it like that, right? And so whenever you're doing these not stirred versions, you want to put the things on the opposite side. So it's sugar and water. And so, we got some waters here on the other side, and make sure that the water or whatever your liquid solvent is, you draw more of it so that you can show that separation. And so here, if it's not stirred, right, they're going to just be divided. Now, do note here that sugar has OC bonds and OH bonds. And remember, the most electronegative atom is fluorine, but the second most is oxygen. Oxygen, I think, has a value of 3.5 or so. You can take a look at your electronegativity chart, and you'll have one for your test, but it's true. O has an extremely high electronegativity, and so if you have an OC bond, that's going to cause this molecule here to be polar. And actually, that OH bond is also going to cause that molecule to be polar. And so sugar is polar, and therefore charged. Water, as we mentioned, is also polar, and therefore charged. And so, are these miscible? They are, right? They're going to mix. They're going to be able to mix, like dissolves like. And so they're miscible. This is a solution. And so when we draw it, you're going to draw the C6H12O6s getting separated and spread out by the water. Do draw for your test at least 2 of each of these. Because otherwise, right, if you only draw one, how am I going to know if it got separated, right? How are you going to be able to draw it out that it got, separated out? You'll say, oh, well, I was trying to show that it got separated. But you can't, right? You have to draw it at least 2 to show that they got separated. And so here, they get separated, they get dissolved because of the polarity of each. And so that's how you do these problems. You determine, is it polar, is it non-polar, is it ionic, right? And like dissolves like. And then you just fill it out as such. So we'll do one more, salt and ethane. Salt is ionic, as we've mentioned, and so therefore it's charged. Ethane, you really want to draw this one out. Ethane is going to look something like this, as it says here, C2H6. And so that looks like this. And let's draw 2 of them. And so then we have the lattice structure. And let's just do a couple more ethanes. Oh, sorry, also, my bad. I didn't draw a lattice structure. All right, there you go. That's better. They're all together like that. And then there you go. So now we're gonna now we're going to take a look at ethane. Right? And ethane, remember, C and H, one of the things that I honestly recommend you memorize is that CH, that electronegativity difference is 0.4 or 0.35, something like that. Right? And so that's less than 0.5. CH bonds are always nonpolar, and this is only CH bonds. Ethane is only CH bonds, and so it's nonpolar. You could go through this whole flow chart, right, and look up the electronegativity values to confirm what I'm saying, but it's nonpolar, and so therefore it's not charged. And so if you have something that's charged with something that's not charged, are they going to dissolve? No, right? There's not going to be any dissolving. Charged cannot get dissolved by not charged, and so therefore they are immiscible. They cannot be mixed. And so therefore we're going to have something like sand water. We're going to have like the salt just being at the bottom and the ethane just kind of surrounding it. And so they're going to be a heterogeneous mixture. We're going to have two parts, immiscible. And so therefore the stirred looks exactly the same as the not stirred. Even though we stir it, it's just going to become the same thing again. And so now I wish I hadn't drawn as many ethanes, but it's okay. It's better to draw too many. I mean, don't go overboard, right? But you know, make sure it shows your point. So yeah, there you go. So this is an example of something that's immiscible because the charges aren't the same, and so therefore they don't dissolve one another. So that is 9.2. Why don't only some things dissolve and how you do these problems. Hope that helps. Let me know if you have any questions.